Now that we have the intuition of how CTL connectives are interpreted, the formal semantics will be a mere formality, so to speak. Given an LTS M and a state S in it, we define what it means that M in S satisfies the CTL formula phi. Or, an alternative way to say this, phi holds for M in state S, written like this. By the way, this is the same notation to the one we used for LTL satisfaction by an LTS. Note that the satisfaction relation considers not only the LTS M and the formula phi, but also a current state S, which, as we've already seen in the informal explanations, will evolve during the evaluation of the temporal connectives. The definition of the satisfaction relation is performed by traversing the formula recursively, following its syntactic structure. If the formula is an atom A, then satisfaction just means presence in the labeling set. Then, if the formula is constructed by putting together one or two smaller formulas by means of a propositional connective, the semantics is the expected one. For example, not phi is satisfied just in case phi is not satisfied. Phi or psi is satisfied just in case one or the other is satisfied, etc. Moving on to the temporal connectives, let's start with the two next base connectives. For all next phi holds, just in case phi holds for all next states. That is, for all immediate successors S prime of the current state S, according to the transition relation in the LTS. And similarly, for the there exists next connective, just that we don't request phi to hold for all next states, but only for some next state. In other words, we want that from the current state S, there exists a next state S prime where phi holds. Now let's move to the interesting temporal connectives. As usual, whenever we write a path pi, we assume that it has the form S0, S1, S2, and so on, just for the sake of having a way to indicate its states. First, let's consider the two variations of eventually. For all eventually phi holds, just in case, for all paths starting in the current state S, there is a state where phi holds. That is, there is an index I such that phi holds on the ith state on the path. So we use indexes to identify states on the path. There exists eventually variation is the same, but we don't request the property to hold for all paths, but rather for some path. There should exist a path and a state on it where phi holds. Now, the two variations of always. Their semantics differs from the two variations of eventually in the same way as the LTL always differs from the LTL eventually. For all the paths that we consider in the for all variation, as well as for some paths we consider in the there exists variation, we want phi to hold not on some state, but on all states of the given path. Hence the use of for all I rather than there exists I, where I is a numeric index of the state on the path. Finally, we have the two variations of until. For all until, we want something to happen on all paths starting from the current state S, and what it wants to happen on each of these paths is, of course, the until behavior. There should exist an index I such that psi is true on the I state, and phi should be true in the meantime, namely on the jth state for j smaller than I, on each of the j states for j smaller than I. And there exists until variation wants the same until behavior to happen, not for all paths, but for at least one pass starting from the current state. This concludes the recursive definition of the formal semantics for CTL formulas. After we define the satisfaction relation, we can now define formula equivalence. Two CTL formulas are equivalent, written like this, using the equivalence symbol, if they are satisfied by the same LTSs in the same states. More precisely, phi is equivalent to psi if, for all LTSs M and states S in them, M in S satisfies phi if and only if M in S satisfies psi. Remember that we had also defined formula equivalence for LTL, but we did that referring to satisfaction by individual sequences rather than LTSs, and later showed that the property extends to LTSs as well. Here, for CTL, we of course must use LTSs directly, since the CTL semantics is defined directly on such structures. Here are some CTL equivalences that I leave you as an exercise. Proving them, even very informally by drawing a hypothetical tree and indicating what happens, is a good test for your understanding of the CTL semantics. Especially if you can see why the last equivalence is true, that means you have a pretty good grasp of the semantics.